Alright, hello everyone. This is Orion's brightest star, and today we are going to be looking at some more topics in curves, specifically acceleration and reparametrization. So we begin with a couple of definitions. So we define v of t as gamma prime of t, where we suppose that gamma is a mapping from an interval I to Rn. And we suppose that it is a regular curve. So this mapping V we call the velocity function. Similarly, we can create another function A of t, which is gamma double prime, and we call this acceleration. So there's a little bit we can do with this. Let's start with our first proposition. And it has to do with the derivative of the speed. So that is, recall that the speed is just the norm of the velocity, where we define the norm as in the previous video. And as it turns out, it is the inner product of the acceleration and the velocity over the norm of the velocity. So what does that look like? Let's say we have a curve like this, and we're looking at this point here, and this is v of t, and this is, actually, you know what? Let's make this a of t. This right here is simply the component of the acceleration in the direction of v of t. So that would be this arrow right here, where that is a right angle. So it would be this. You know what? Let me draw this right there. It would look like that. So let's prove it. We begin with, the proof should just be a fairly straightforward computation. So we take the derivative. The norm is the square root of the inner product of v of t with itself. So what we can do is we can use the chain rule. So first we're differentiating 1/2 the inner product of v of t with itself to the power of -1/2, because we're differentiating this whole thing. And now it's time to differentiate the inside. So now we have to use the product rule, because this is the inner product, and we get v prime of t, vt, plus vt, v prime of t. And remember that in the real numbers, the inner product is symmetric. So we have 1/2 and then over here we have 2 times v prime of t, v of t. So we can cancel these out, and we get let's turn this into the denominator. We get v prime of t, vt, that's this, over v of t, v of t, and power of 1/2. That's that. But remember, v prime of t is equal to a of t, so we get this. And remember that this is equivalent to the norm of v of t by the definition of the norm. And if we look at our proposition, that is exactly what we are supposed to get. And therefore, our proof is complete. So that's all on the acceleration. Let's talk about reparametrization. So first up, let's define something called the trace. So if we have a regular curve, gamma, from I to Rn, the image of the curve is called the trace. So it's the set of all points gamma of t where t is in I. So if we have a curve that looks something like this set of points that's the set of points that is that are on the line, that will be the trace. It's just the set of all those points. Now let's talk about reparametrization. So if we have a regular curve gamma from I to Rn, a reparametrization is a function of the form that equals gamma composed with phi, which goes from another interval to Rn. This is an interval, and the function phi is a function from our second interval to our first interval. So, and this is smooth and bijective. And what that means is it has an inverse. It has an inverse. So this exists. There exists that. And the inverse has a derivative as well. So the inverse derivative also exists. And obviously, so does the derivative. Yeah, I believe we will see soon that this is called a diffeomorphism. But if I'm wrong, I'll correct myself in the comments. Anyways, so we can think of this as a sort of, let's say we have two intervals, like so, and we have a curve like that. This is our normal gamma. It takes us from I to, let's make this Rn. It takes us from I to Rn. This is our function phi. It takes us from the second interval to the first interval. And since it's bijective, it can, if we think of it as like if we think of this as like time, it could be going forward, it could be changing speed, it just can't stop. It could go backward. It just can't go backwards and then forwards, or forwards and then backwards. So um, that should help give you some sort of clarity of mind when it comes to reparametrizations. And then finally, we have the second gamma, which is the composition of the phi and the gamma. So that's phi comes first, so it's to the right. So this is the idea behind a reparametrization. We're taking a regular curve which has interval as its domain, and we're making it such that it has another interval as its domain. Now, some more definitions. Gamma tilde is orientation preserving if the derivative of phi is greater than 0. It is also orientation reversing if phi prime is less than 0. So if it's orientation preserving, it's going to be going, you can think of it as it's going to be going forward. And if it's orientation reversing, you can think of it as going to be going backward. This is all just like a very crude analogy. It's just supposed to help you gain like a sort of intuitive understanding of reparametrizations. So now let's move on to a proposition. A regular curve, gamma, can be reparametrized by arc length. So, how are we going to prove this? We want to find a way to reparametrize it by arc length. So, a natural way to begin would be to consider the arc length function. So, this is our arc length function, as you might recall from the first video. And if we take a look at this, we have that S prime of t is equal to the norm of y prime of t because of the fundamental theorem of calculus. You can think of it rather intuitively as like the derivative is like sort of canceling out the integral, so we get this. And we know that this norm is not equal to 0 because gamma is a regular curve, so gamma prime is not going to be equal to 0. Therefore, we have that S is a smooth bijection such that S prime does not equal 0. It's clear then that S has an inverse function, we're going to call it phi. And just for the record, let's say that S maps to a subset of R, which we're going to call a second interval. This works because a function phi is going to be the inverse of the arc length function, as we will soon see. So now we have that our reparametrization is equal to the composition of gamma and phi. Remember that phi comes first, and that's why it's to the right. So it goes from a second interval to Rn. Let's take a look at what happens when we compute the speed of our reparametrized curve. So by the chain rule, we have that this is equal to, remember outside function first, gamma prime of phi of t, there's two parentheses, times the derivative of the inner function, which is phi, so phi prime of t, and that is equal to, we can take this phi prime out of the absolute value. We're just assuming that it's orientation preserving, and we get this. But remember that S is the inverse of phi, since phi is the inverse of S. So this is equal to 1 over S prime of phi of t but remember that S prime of t is equal to the absolute value of gamma prime of t. So since we have phi of t in both arguments, we have this, because S prime is equal to the norm of gamma prime, and that is equal to 1. Therefore, this is equal to 1. So what we're saying is the speed of a reparametrization is equal to 1. And therefore, we have found a reparametrization for any regular curve that such that its speed is equal to 1. And therefore, we have completed the proof. Now, let's take a look at some examples of curves. So a closed curve is a regular curve from an interval, a closed interval, from a to b to Rn, such that gamma of a equals gamma of b, and gamma prime of a equals gamma prime of b, and so on. A simple closed curve is a closed curve that is 1-to-1 on the interval between A and B, but not including B. So, what would a simple closed curve look like? It would look something like this. Simple closed curve. Would this be simple? It would not, because it's not 1-to-1 over there. So this is just a not simple closed curve. What about this? But this is an angle. That is not closed because, as you can see, the derivative at A, which we can interpret as a left-hand limit, looks like this. But its derivative at B, I'm just assuming it's going from A to B like that, is that. So the derivatives do not match. So this is not closed. And obviously something like this is not closed, not closed. Even in like the typical sense of the word, it's not closed. So those are some examples of curves, and let's say we have you know what? Let's write this down as proposition. So our proposition here is going to be an if and only if statement. And that means that we have to prove both ways. So a regular curve is closed if and only if there exists a periodic regular curve. We're going to put a gamma with a hat from R to Rn with period B minus A such that we have this for all t in A, B. So let's prove this. The proof is not in the book, and I have not prepared a proof, so I'm going to be doing this right now as we speak. So let's see what I can do. So let's start by assuming that we have a regular curve that's closed. And then let's move to that there exists a periodic regular curve. So what can we say about gamma? Well, gamma A equals gamma B, gamma prime of A equals gamma prime of B, and so on. So what we need to do when we see these when we need to prove that there exists something, is we need to construct something that follows these criteria. So let's say we have gamma hat of t equals, let's say gamma t if A is less than or equal to t is less than or equal to b, gamma of t plus a minus b if b is less than t is less than b plus b minus a, I think. 2b minus a. Let me check if that's 2b minus b is b minus a plus. Yes, that works. And so on. And we also have gamma t plus b minus a if we have oh, whoops. If we have, let's start here, a is greater than or equal to t, which is greater than or equal to 2a minus b, 2a minus b, and so on. So, what can we say about this curve? It is like, it's like a massive piecewise um, function, but it's clearly periodic with period b minus a because we have that gamma hat of t plus b minus a is equal to, oh, you know what? We'll do one even better. Oh, t plus n times b minus a equals gamma hat of t, where n is an integer and is it regular is the question. And we know that gamma is a regular curve, so at every point except these boundary points, we know that it's going to be smooth and effectively regular. We just have to check these boundary points, and as it turns out, it's because gamma of a plus b minus a equals gamma b, for example, and then gamma a equals gamma a. But we also have that gamma a equals gamma b, and we also have that gamma prime of a equals gamma prime of b. So at these boundary points, they're effectively smooth. So this is not like the most vigorous proof, but this is just supposed to sketch like an outline of how one would be expected to go about this sort of proof. So now we have that. Let's say we've proven it in one direction. Now let's prove it in the opposite direction. So we have a periodic regular curve such that that is equal to that, and let's say we have we have that gamma prime of A is equal to gamma prime of B. And the reason why is because gamma hat has period B minus A. Furthermore, we also have that gamma hat prime of A equals gamma hat prime of B for the same reason, and so on. Therefore, gamma of A equals gamma of B, and gamma prime of A equals gamma prime of B, and so on. So we can say that by the definition of a closed curve, gamma is closed and also regular because gamma hat is regular. So once again, this is not supposed to be rigorous, it's not supposed to be perfect, but this is just supposed to be a sketch of how one would go about approaching these sorts of problems. And that's basically all I have for today. I'll see you in the next video.